All right, what's an sp3 carbon? What's an sp3 carbon? What does it mean to be an sp3 carbon? Come on now. I know you guys all sat at home. No air conditioning. No lights. By candle. Studying organic. I was going to ask you about sp3 carbons, but then I thought, oh, classic compounds is better. What's an sp3 carbon? What does it mean to be sp3? What? Tell me more.
Bond angle 109.5.
That's a tetrahedral. What's it mean to be sp3? What does it kind of mean? Give me an idea what it means. The carbon will have 4 bonds. All carbons have 4 bonds, though, right? What does it mean?
All 4 are bonded.
Pardon me?
All 4 are bonded.
Even if you're not sp3, you can still have 4 bonds that are bonded, though. What does it mean to be sp3? What? You'll eventually have 8 when you have all your bonds, right? But what does it mean to be sp3? If a carbon is sp3, tell me something about it.
Bond angle of 109.5 degrees.
That's true. That's tetrahedral. But what does it mean to be sp3?
25%, 75%.
Right. So sp3 orbital has 75% p characteristic and 25% s. It means that the s orbital and the 3 p orbitals of period number 2, or shell number 2, have all hybridized mathematically together, right? And the result of that, as you guys pointed out, was a bond angle of 109.5. That's what explains the bond angle. You get these hybrid orbitals, right? Now, if I have an sp3 carbon, it looks something like this, right? And I said the sp3, they look kind of like that, right? Maybe put a hydrogen there. Okay? And there's more than just those two. Whoops, that's not very good. Try that again. There's 4 of these bad boys, right? And some of them are coming out towards us. Some of them are going back into the plane. And there's a hydrogen here, and there's a hydrogen there. There we go. So that's like a molecular orbitals of an sp3 carbon. That's methane, CH4. No problem, right? You remember this now, right? A little bit. Okay, good. I'll take a little bit. And I said, okay, these are sp3. So this carbon, you could also say, if you wanted to, is an sp3 carbon. Oops, sp. The hybridization state of that carbon is sp3. What's the easy way to know? Everybody is single bonded. All the bonds to carbon are single bonds, so it must be sp3. Okay?
Why?
Why what?
Why is sp3 a single bond?
Well, we're going to get to that. That's a great question. In fact, let's get to it now. What's sp2? Come on now. What? That's the bond angle. What does it mean to be sp2? Not 1550. sp2. So there's s and 2p. So it's a third and 2/3, right? So you're 2/3 p, 1/3 s. And the other p orbital does what? It doesn't float around, but it remains unchanged. Remember we talked about that? sp3. We have the s orbital plus the 3 p orbitals equals 4 sp3. And they look kind of like this. 4 times. Right? So all 4 of these orbitals get involved to make these orbitals here. I know we had 2 weeks off, guys, but we really can't go back. We have to move forward. We don't have time. Okay, so it's important that you guys get this stuff, right? So sp2 is 1. So remember, there's always 1 s and there's always 3 p's, right? And that's going to give us, if we have sp2, we're going to have 3 times sp2, and they look kind of like this. Well, better than that. They look kind of like that. You'll get 3 of them plus a p orbital. You get 1 unhybridized p orbital. So sp2 means that the s and 2 of the p's will mingle, mathematically combine, but you'll be left with that lone p orbital, right? Doesn't get destroyed. It just doesn't get changed.
So the initial, I guess the reactants is always 3 p orbitals.
Yeah, you must have 3. You always start with 3.
Whether it gets used or not, that's
Well, it'll get used, but whether it gets hybridized.
hybridized or not.
Right. But they will get used, right? Because we said this was a great example of an sp2. We said like that, and then we drew like something like this. And I said these sp3 are going to bond together, right? sp3, like that. And then I said, okay, behind here and coming out this way, sp2, sp2, right? Remember that?
Yeah.
Starting to come back to you? And then there would have been another one here. Right? And these are sp2. Oops, sorry, sp3 there. I screwed that up. There we go. And
It's all SP2, right?
sp2. Okay? And then we said, okay, so there's my 3 sp2 orbitals, right? 3 of them. I used all 3. I still have to use that p orbital, right? Yeah,
What is the thing under 4 times SP3?
that's what the sp3 orbital looks like. It's got a little short, little nubby part and a big fat part on the other side.
So we have to put that on under all of them?
I,
That's under 3 too?
I would. Yeah, they look kind of similar. If a computer does the modeling, you can see that the sp3 is actually shorter and fatter, but I'm not, I'm doing my best here. I'm not going to measure yours either. Now, the p orbital is at what angle to the sp2 system? 90, very good. Remember I showed you a model of that? And these p orbitals are going to overlap like this and overlap like that. And that's going to form another bond, right?
Yeah.
What kind of bond is that? This is a pi bond. So there's a half a pi bond up here and a half a pi bond down there. Oops. 2 pi. What kind of bond is this? It's a sigma bond. Very good. What is the difference between a pi bond and a sigma bond? If you had to describe it, what would you say the difference is?
Sigma bond is stronger.
They are stronger. Why? They're what? They overlap. Much more efficient overlap, right? So they overlap head to head, right? One sp3 orbital, another one, come head to head. Get really good overlapping, right? And pi bonds, they stand next to each other, shoulder to shoulder, and they have minimal overlapping, right? Now that doesn't mean non-existent overlapping, right? It just means minimal. Okay? So they're weaker. Pi bonds are weaker than sigma bonds. Are you with me together? We all good on this so far? So any kind of double bonded molecule, such as this one, here's an alkene. This carbon here is sp2. And so is that one. How do I know that? They have double bonds. Anytime an atom has a double bond, well, anytime a period 2 element has a double bond, it's sp2. Okay? Because it must have 1 sigma and 1 pi. It must have. Okay? That's how it works. So this sigma bond and the pi bond is the top and the bottom. Okay? That's how bonding works. Everybody with me on that a little bit?
It has to have 1 sigma and 1 pi, you said?
Every double bond will have 1 sigma and 1 pi, yeah, for period 2 elements. Period 2 elements, like carbon, nitrogen, oxygen. Not sulfur. Sulfur and other atoms can do a different kind of bonding. Now, that's sp and sp2. sp3 and sp2, right? We talked about single bonds, talked about double bonds. What's left? Triple bonds, right? So, if we know a double bond has a sigma and a pi, what do you think a triple bond will be made from? 2 pi's and 1 sigma. Very good. Self high five. There you go. I mean it when I say that. Right? Good. Very nice. A triple bond will be called sp hybridized. It'll have 1 sigma bond and 2 pi bonds. And that'll be a triple bond. Now, these things get a little hairy. Not to think about, but to draw. The drawings can get a little bit, well, they just get a little intense. Let's just say it that way. Now, let's consider sp. So remember, we have an s plus 3p orbitals, right? There we go, an s and 3 p's. So we're going to take s and p, we're going to mix them together. So this one, say, and that one, we're going to mix them together somehow mathematically. And we're going to get 2 times sp, 1s, 1p. So it's 50% s, 50% p. So it's going to have more p characteristics. It's going to be shorter and fatter than sp2 and sp3 because it has more circular character, shall we say, or spherical character. But that means we must have 2 p orbitals left over, right? There must be 2 of them. Because here we start out with 3. We used up one of the p orbitals, so we have 2 left over. Make sense? All right. So let's consider the simplest sp molecule. That would be this one. It's an alkyne. So we know, and I'm going to tell you now, that those carbons are sp. Their hybridization is sp. The easy way to tell is there's a triple bond. sp, any group 2 element that's triple bonding will be sp. Okay. Now here's what the sp looks like. Here's what sp looks like. There's a carbon. There's a carbon. And here's my first bonding. That's a sigma bond. This is an sp orbital here. This is an sp orbital there. And that's a sigma bond, head to head. Good orbital overlap, very strong bond. The other sp orbital, because remember there are 2 of them, believe it or not, is 180 degrees. So it's linear. Okay? It's linear. 180 degrees. Here's my second sp orbital. Again, it's a little bit off, but it's supposed to be linear. Okay? So the hydrogen and the 2 carbons and the other hydrogen, all 4 of these atoms are lined up in a linear fashion. Now, here's one of my p orbitals, and here's another one. So there's one of my pi bonds right there in pink. So the top part is half of a pi. Here's 1/2 pi down here at the bottom. You can call that pi bond 1 if you want, or call it pi bond pink, however you want to name it. Now, we haven't used up all the orbitals yet. We've used up these 2. We've used up that one. But what about the other one? We've got one more p orbital left, right? Right? Yeah. What angle do you think the p orbital will be from this one? What angle would be the most logical for it to be? 90. Because that's as far away as it can get, right? So the other p orbital is going to be 90 degrees. Now here's where it gets hairy. It's hard to draw this. I've been doing this for years, and it's kind of hard to draw. Because, you want to make it look neat, right? So I'll do my best. Please do not critique my drawing. I'm very sensitive. Everyone laughs at that. All right. Make it nice and thick. And then make a little dotted line back that way. I'm trying to show the orbital coming at us. All right. Now, again, in your book, there's beautiful computer drawings. Online, there's lots of beautiful drawings of these things done by computers and by artists. Me, I just do my best. Okay? So there's one of my p orbitals that are coming out and in. And here's the other one. Give it a nice little thick line, and then there you go. I'm trying to show it going out and then back in. I'm trying really hard to show the third dimension, if you will. And they will overlap back here. Notice how I didn't draw lines through that p orbital. I'm trying to show that this p orbital is in front. Okay? This p orbital is behind, that one's in front. And then here, there's overlapping there. All right, now it's kind of messy, I know. I did my best. But I have a model kit. Model kits, they save everything, right? They're the best. Don't forget, this model kit, or ones similar to this kit, I should say, are available at the library for you to borrow. You don't have to rely on me. All right, let's build. Oops, wrong hybridization. Let's build. All right, here we go. All right, so here we go. I want to make just a sigma bond between these two carbons, okay? So there we go, sigma bond. And I'll make the hydrogen bonds right to here, okay? So right now, I've just put in the atoms. Whoops, it was easy to break that one. Now, hydrogen, carbon, carbon, hydrogen, okay? Linear, all the way. Now, if we put in the first p orbital, let's make it, I don't know, some weird white color. Weird white and turquoise, I guess. And let's, get some more sticks here. What did you do today? I built models out of sticks. That's great. All right, so there's one of my p orbitals there, right? Notice it's 90 degrees from the sigma bonds, right? And let's build a pi bond over here, or sorry, a p orbital over here. Come on now. There we go. There we go. So as you can see, sigma bond, half pi, no problem, right? Seen that numerous times, right? At least twice. Now, let's build the third dimension, the other pi bond, the second pi bond, if you will. And let's make it sacre bleu. This is terrible. This is tragic. It's tragic. All right. Hold on to that, will you? So it doesn't fall apart again. I'm old. I don't want to bend over again. Oh, how about blue and black? There we go. Hold these for me, will you? Thanks. All right, hold still. It's only hurt for a minute. There we go. And there we go. Probably not a good choice of color, but that's fine. Thank you. Now, as you can see, there's a blue little straws coming towards you, yeah? That's your second p orbital. It's coming right at you. Okay? Here we have the black and white ones. They're coming in behind you, right? So here's a sigma bond. Top of a pi bond, bottom of a pi bond. That's the one in pink. This one here is coming at you, the front of it, and the back of it. That's the one in orange. Okay? So this, even though it's linear, it's still three-dimensional, right? There's a pi bond here and a pi bond there. And it's, of course, in the back too, right? Are you with me so far? So if I were to ask you what's the stronger bond, a double bond or a triple bond, what would you say? Why? It has more overlapping, right? There's more orbitals that are overlapping, right? Makes sense? Pretty neat, huh? If I were to ask you what bond's shorter, single bonds or triple bonds, which one's shorter? Why are triple bonds shorter?
Because there's more force to pull together.
No. Good try, though. Why would a triple bond be shorter than a single bond?
Because it's a lot of overlap.
Right!
Half sphere.
Right. Because sp2 orbitals are shorter because they're half spherical. They're half the elongated dumbbell, but they're also half spherical too, right? So this bond right here has a lot of S character, right? Which means it's a lot shorter than an sp3. Make sense? See, all this stuff makes sense? Thank you. You see why I don't want you using tables? Because you can just look that up, right? Triple bond versus single bond, let's look it up. You can get the bonding, you can get all that stuff. But I don't want you to look at tables because it's all logical, right? If this is half S, it must be short and stout. If it's a third S, it must be a lot longer and thinner, right? Make sense? That's what we're looking for. We're looking for logical determinations of complex problems. Isn't that fun? Isn't that awesome? Right? I expect you to know how to draw these. Oh, yeah. Guaranteed question on an exam. Now, maybe not that particular molecule, but one just like it. Okay. Let's have some fun. What if I drew something like this? All right, and I said, for each atom that's not hydrogen, because don't worry about the hydrogens, for each atom that's not hydrogen, indicate the hybridization state. What I'm looking for is it sp3, sp2, or sp? Don't yell out your answers, just think about it for a minute. So much it costs for your stuff back. I'm just joking. Just kidding. What's the hybridization state of each atom that's not hydrogen? Don't worry about hydrogen. I just want to know about the carbons and the oxygens. What is it, sp3, sp2, or sp? That's what I'm looking for. You don't get to draw anything, just indicate what it is. Take a minute, contemplate, commiserate with a friend. Ah, die. Sorry, there's a bug. I guess we could start there. Yeah, we'll start there. All right, how we do, guys? I'll point, you yell. What's the hybridization state of that carbon? sp3. I didn't say it was right. I just agreed with you. That's what you said. What's the hybridization state of this carbon? It's probably the same, right? Maybe, maybe not. How about that oxygen? sp2? How about that carbon? sp2. What do you guys think? Anything wrong there? Sure? What's wrong with the oxygen? You think it's sp? Sure about that? No. Okay. You sure about this one? Who's sure that's right? Who's sure this one's right? So there's more people sure that that one's right than this one. They're the same carbon. Come on now. All right, so you guys are, who's sure? Raise your hand. Be brave. All right. Who's sure that one's right? 100% sure. One person. Two people. Three.
No idea. That's not right.
Who's sure this one's right? If you're sure those are all right, you're absolutely correct. Those are all right. Nice job. Round of applause. For you, not for me. Nope, nothing even for yourself. Okay. No, hold on. I have a method to my madness. Trust me. I'm going to explain why. Don't worry. So who was 100% right? Who got them all right? 1, 2, 3. Few people did, right? Who was confident they were right? Not the same people. That's interesting. Usually the same people. All right. Big problem in this class, confidence. Students they'll put the right answer down, and they'll erase it, put the wrong answer. I've seen it all the time. Happens every exam. Stop doing that. Kills your score. Okay? Confidence. You have to have confidence in what you're saying. Now, I didn't expect anyone to have confidence in this because you just learned it, right? But you have to have confidence. Confidence is king. If you don't know what you're doing, you have no confidence. If you know what you're doing, you have extremely high confidence, right? Don't get arrogant, though, because, arrogance will kill you. Now, why is it sp3 for the people who got it right? For what? For sigma bonds. That's what I'm looking for. 4 sigma bonds, right? And that usually, almost always, represents itself as 4 single bonds. But I want you to say sigma from now on. Sigma bonds. Okay? How about this carbon? Why is that sp2? It has a sigma bond and a pi bond. Right? How do we know that? Well, it's a double bond. Double bonds are always made of 1 sigma and 2 pi. Sorry, 1 sigma, 1 pi. Pardon me. Right? They're always made that way.
What about the other bonds with the other carbons? We're just looking at
You mean here?
the carbon with the oxygen, the carbon in
Yeah, I'm looking at this carbon here. It's got 1 sigma and 1 pi and a sigma and a sigma.
So 3 sigmas and
1 pi, that's sp2. Very good. Oxygen, I kind of threw you a curveball. Never showed you anything about carbon and hydrogen so far. But you nailed it. It's sp2. How do I know that? 1 sigma, 1 pi. And it's on period 2. Oxygen's right beside nitrogen, right? Is that fun or what?
Wait, so
What do you mean, no? Okay, what's not fun about it?
Because it's complicated.
I know, right? We're going to learn it, aren't we? Let's do another one. Yeah, see? Look how excited he got.
The middle C.
Yeah.
Middle carbon.
Yeah.
It has a double bond, but also, so it doesn't matter that it has other sigma bonds. It just
Nope.
has that one pi
It has to have 3 sigma, 1 pi. That's sp2. If it has 2 sigma, 2 pi, that's sp. Are you with me? If it has 4 sigma, that's sp3. All right?
3 sigmas and 1 pi.
Right.
That's
sp2. Right. Because remember, sp2 means that the s and the 2 p's hybridized, right? So there's 3 orbitals there, right?
So there's always, sorry, because in this case of carbon, there's always going to be the 4 bonds, just
Always 4 bonds to carbon.
like
Yep.
the ratio of sigma to pi, which is
Right.
16, okay.
Right.
So the lone pairs on the oxygen are those sigma bonds?
Great question. Let's talk about that. Let's just make an easier example. Let's get rid of those carbons. So there's an easier example. We get rid of the carbons, the methyls, the CH3s. So this carbon here is what hybridization? It's sp2, right? And that oxygen is also sp2. Let's draw it and prove it to ourselves, okay? Because there's a great question about where these lone pairs are. Like, where are they? I mean, we draw them on the molecule, but what orbital are they in, right? It's a great question. So let's draw the oxygen here and the carbon over here. So this is carbon right here. It's going to be that carbon right there. And the oxygen's right here, okay? So they're sp2. We know that that's a sigma and a pi bond, right? Everyone okay with that? Sigma and a pi? So let's just draw the sigma bond first. Let's draw that first because it's kind of the easier one to get out of the way. Sigma. Sigma. That's an sp2, right? And we know the sp2 orbitals are, you guys already said it, what angle? 120. Very good. You guys already said it. So I'm trying, there you go. I did my best to draw them 120 from each other. Is that okay?
The sp2 are 120.
They're 120. Yep. But now, and we can put the pi bond here too, right? So let's go ahead and draw the, everything here should be familiar so far, right?
Yes.
Kind of, we just did it, and we did it 2 weeks ago. Don't we just feel like we're starting over, right? I totally feel like I'm just meeting you guys for the first time. I know, right? I'm that guy. So there is the sp2 carbon. I left the oxygen alone. I didn't touch it. Because now we're going to go after it. But I'm going to ask you some questions, and I want you just to think logically. This is sp2. That's correct. This is also sp2. So what's missing off this oxygen? The p orbital and? No, not the s orbital. sp2 orbitals, right? How many are there total? There's 3 total, right? There's going to be 3 total sp2 orbitals, right? Everybody agree?
Why?
Because sp3 has 3 total sp orbitals, sp2 orbitals.
Wait, say it again.
If you okay, everyone say sp3. Just say it. It's s1p3. Add up the numbers. 4. How many sp3 orbitals are there? 4. sp2 is s1p2. Add up the numbers. How many sp2 orbitals are there? sp, s1p1. Add up the numbers. How many sp orbitals are there? 2. See how that works? Me and you. sp3. Just write it down on your page. sp3. All right? Now, it's just like in math, right? There's no 1 by the s. It's supposed to be s1p3, but we don't put the 1 in, right? So you have to know it's there. So now take the 1 and add it to the 3. So you're going to have 4 sp3 orbitals. Okay? Do the same thing for sp2 for sp. Okay? That's how many hybrid orbitals you're going to have. That's like a little trick to remember. Okay? Is that okay now? Better? All right. So if this is sp2, how many sp2 orbitals must there be? 3. What angle are they from each other? 120, right? So does it stand to reason then that the orbitals for this atom are going to be basically the same as that one? Does that stand to reason? They're both in period 2. They're both sp2. They're going to look extraordinarily the same, right? So I should have an orbital coming to the front, right? And orbital going to the back, yes? Anybody else?
No.
No, there's not. It's just me and you, man. Okay, so this is sp2, right? And sp2 as well. So where are the lone pairs? What? No, they're not the lone pairs, but they're where the lone pairs live.
Are they on the p orbital not being used?
Nope.
They're on the sp2 orbital?
They're in the sp2 orbitals, right? Now, it's a good question. Or someone said, couldn't they be in the p orbital not being used? It's a great question. The trouble with that is that we know the p orbital here has to be used. How do we know that? Because it's making the pi bond, right? Right? Okay, come on, guys. Say yes or no. Say something. Don't just sit there. So this is like not a spectator class. It's a, you talk to me class. So there must be a p orbital here, right? Because it's sp2, right? Okay. What are bonds made of? What do you have to have a bond? Orbitals and electrons, right? So if these orbitals are making a bond, which they are, right? There must be electrons in them, right? I haven't drawn them in, but they must be there, right? I drew them in for here so you can see them. Right? That's why the lone pair can't be in the p orbital, because this p orbital is bonding. So it's already got 2 electrons in it. Right? They have to be in these orbitals. Is everyone okay with that? Now remember back in general chemistry when you took Vesper theory, right? Vesper theory said treat a lone pair like a bond. Right? So if something has one bond, or a double bond, say, how do I want to do this? Has 3 single bonds in a lone pair. Nitrogen example is a great example of that, right? That's not tetrahedral. It's starts with a P. Found them in Egypt. Pyramidal. There you go. I know what the next quiz is going to be about. We're going to hit Vesper theory. Pyramidal or pyramidal, however you want to say it. Okay? Remember all that from Vesper theory? No? Okay. Well, it's in Vesper theory. You took it in General Chemistry 1. Just so you know. You might want to review that. Anyway, so this is sp2. Here's the pi bond. Here are the sp2 orbitals, and they contain the lone pairs. So the lone pairs are 120 degrees from each other. Is that okay? 120. So you may have seen me do this. I try to avoid doing it until you guys can understand it. But now you understand it. I put the lone pairs there. And when I draw my Lewis structures, I usually put them there. Why? 120. I'm trying to show the angle, even in my Lewis structure. Okay? It's hard. I get it. I know it's hard. But you're going to learn it. I have faith in you. Do you have faith in yourself? Oh, jeez. I can't win that battle. Do you have faith in yourself that you can learn this stuff? It's not that hard. Trust me, it's not that hard. All right, let's do another example. Yes, we will do this. No, not C. O. There you go. Ha! Any non-hydrogen atom. Don't worry about the hydrogens. I don't care about them. I care about the carbons, the oxygens, and the nitrogens. Think about it for a minute and don't yell out your answers. Just write your answers down or whatever. Which ones are sp3, which ones are sp2, and which ones are sp? I'm not saying that all 3 of them are in that either. Maybe commiserate with a friend. See what they think. So, how we do? Better? Who's confident this time? Much better. Which one's the hardest one, do you think? The nitrogen or the oxygen? Not the carbons, right? The carbons are the hardest one. All right, let's start with the carbons. Who thinks carbons are hard? I saw you shaking your head.
Me?
Yeah.
No, that's
Oh, she's pointing you out.
from another area.
Wow. No, I looked at you. You were like, yeah, they're hard. I'm like, okay, let's talk about them. Who thinks the carbons are hard? Seriously. Nobody? How about the oxygen? Okay, a few folks. Okay, good. What do you think it is?
Which one? Oxygen or carbon?
That one there.
SP3.
Okay. What do you guys think? You think it's sp3 as well? How about that carbon there? SP. How about that carbon there? Very good. How about that carbon there? I left the nitrogen till last. How about the nitrogen? SP. Very good. All those are correct. Nice job. Very good. Let's talk about the nitrogen. What I normally do in exams, because I don't want to ask you easy questions, right? I want you guys to feel confident and challenged. I'd draw that molecule on an exam and I'd point to that lone pair and I'd say, where is that lone pair? And some of you will be smart and point out saying they're right there. And I'll go, ha ha ha, 0. So let's not say that. I'm asking basically, I would word the question a little better on an exam because I'd have more time to think about it. Basically what I'm asking you is what kind of orbital are those lone pairs in? They're in what? SP orbital. Very good. What's the angle between that lone pair and that triple bond? No. No. 180. They're 180, right? If it's in an SP orbital, right? You guys agreed on that, right? I heard a lot of you said it, right? Right? And SP orbitals are 180 from each other, right? Because the shape of this molecule is linear, right? That's why when I draw this molecule, I draw the lone pair there. I don't draw it here. I never draw it here. That's not right. Doesn't this look strange? Yeah. This looks right because it's 180 from the triple bond, right? This is 90, which is not right. How's that? Is that pretty good? Yeah. All right, take this molecule here at home tonight. Draw its molecular orbitals, all of them. Draw all the pi bonds, all the sigma bonds, draw all the bond angles in, label all the orbitals. Draw the lone pair in. Draw and label all the molecular orbitals for that molecule right there. And don't worry that you're not a Rembrandt. That's not what I'm looking for. Just make sure I can tell what it is. All right? So do your best.
Can we use chem doodle?
No, use your hands. Because on an exam, you can't use chem doodle. But after you do it, you could do it on chem doodle. Chem doodle does a nice job with this.
You want us to write the bond angles?
I would, yeah. It's kind of a review to make sure you guys can all do it. Yeah. And the angle between the angle between all the orbitals too would be good. So remember, like the p orbitals are all 90 degrees from each other, and the p orbitals are always 90 degrees from the sigma bonds, always.
The second one.
Yeah, you can do that one if you want to. It's a little harder. I don't think I would want to tackle that one. Just get messy. But you could do it. It's not- Yeah, draw and label, bond angles, SP2, SP3, all that stuff. Get used to doing it.
Do you have videos on that stuff?
I don't think I do. Not yet, no. but eventually this will get posted.
Suggestions for,
What?
suggestions for videos?
Send me an email and I'll look some up. But as of right now, no.
Khan Academy has a whole organic section to it that kind of explains some of it.
So before we move forward, I just want to review really fast. So for SP3, it has 4 sigma and one sigma bond. 4 bonds or 1 sigma bond. Am I saying that right or no? No, 4 sigma bonds, sorry. SP3 has 4 sigma bonds.
Yeah,
Yeah. SP2 has 3 sigma bonds and 1 pi bond.
right.
And then SP has 2 sigma and 2 pi? Or no?
Yep.
Yep.
hmm
Gotcha.
Well, forget that. I guess I'll have to just go freestyle. All right.
Wait, quick question.
Go ahead.
Where the nitrogen is SP, but why is it SP not SP3?
This nitrogen?
No, the nitrogen on the first side.
That one?
Yeah.
For the same reason that one's not. There's a triple bond, right? So triple bond to grouped period 2 elements always, if they have triple bonds to them, are always sp. It has 2 sp orbitals and 2 pi bonds, or 2 p orbitals.
And then the angle of an SP2 is 120.
Yep.
But SP3 is 90.
No, it's 195.
Bond rotation. In case you can't tell, I'm moving on. Bond rotation. Jot that down. Now, let's think for a minute. Let's contemplate life. If I have a molecule, like the one I'm making here, these carbons are sp3, because they all have 4 sigma bonds, right? Oops, I'm running out of straws here. So we have 1 point of connection between the 2 of them. We have 1 sigma bond between these 2 carbons. Okay? So this is a carbon here. That's a carbon there. Sigma bond between them. 1 point of connection to that carbon. 1 point of connection to that carbon. So what that means is, because there's only 1 point of connection, this carbon and that carbon can rotate independent of each other. Now what do I mean by that? I mean, well, right now, this yellow straw and that white straw are lined up, right? This carbon can rotate independent of that one. Okay? So it can just rotate about the axis, because there's only one axis here, right? Which means it can rotate. This carbon can rotate the other way or the same way, independent of this carbon, because there's only 1 point of connection between the 2. Are you with me? Imagine, if you will, like a pinwheel little kids play with, right? And the little thing twirls around. Okay? That's how it works, yeah? Pretty simple. 1 point of connection. This carbon can rotate freely, and this carbon can rotate freely, whichever direction they want. Okay? As long as it's around the axis. You with me? It's called bond rotation. Happens all the time. Now, what if we have an sp2 carbon? Something like, say, something more interesting. Like, say, this one. Let's build this molecule. It's going to have a double bond in it now. All right, here we go. Building a molecule. Here we go. All right, so there's my sigma bond between my 2 carbons, okay? But now we know it's going to have a double bond. So it's going to be sp2, so there has to be a double bond, right? So I'm just going to build the pi bond. I'm going to leave out the other sigma bonds because they just get in the way. But here, I built a sigma bond, a pi bond here, and a pi bond there. Are you with me? Now, remember, these things are connected, right? On the top and on the bottom. They're actually connected. They're blending together. So in order for this bond to rotate, these bonds have to rotate too, right? Because they're connected. Are you with me? So when this bond wants to rotate, say, this way, the entire molecule is going to rotate that way. This carbon and that carbon have dual connections. One connection here, and the pi bond is also connecting them. So if this bond wants to move, everybody has to move. So the whole thing is going to rotate. So this carbon and that carbon cannot rotate independent of each other. They must rotate in the same direction. You with me? And like that. Okay? Pretty interesting, huh? Because of the connections, the way they're connected. Okay? Now, if double bonds can't rotate independent of each other, the carbons, I'm saying, can't rotate independent of each other in a double bond, the same must be true in a triple bond. Right? The carbons are fastened together 3 times at that point, right? So they're definitely connected. So they can't rotate independent. So single bonds have that special ability to rotate independent of each other, right? So remember, the single bond, carbon on the right can turn clockwise, carbon on the left can go counterclockwise, or vice versa. They can go in the same direction. They don't care. Why don't they care? Because of the way they're connected. Okay? Are you good with that? It's kind of a simple little point, but it's an important one. They can rotate about the single bond where double bonds can't do it. Now, this leads me to an interesting concept. And I sure wish I could show you my slides. My slides are really kind of nice about this. Come on. No, okay. Make sure I spell these words right. Isomerism. Isomerism. In other words, isomer. I-S-O-M-E-R. You've heard of that word, right? General chemistry? Isomer. What's an isomer? Remember that from general? Say that again.
Same amount of protons.
That is an isotope. Good job.
Isomer is
Well, you're... Yeah, those are examples of isotopes, yeah. Or sorry, they kept me saying it. Isomers. Yeah, exactly. What'd you say?
Different compounds with the same molecular.
Oh, you're just reading it from the book? Oh, come on. Really? I'm just joking. All right, yeah, they're the same molecular formula, different molecular shape. That's one kind of isomer. Okay? Same molecular formula, different molecular structure. Let's say it that way. Now, that kind of isomer is called a constitutional isomer or structural isomer. Okay? And I'll just spell constitutional for you so make sure I don't misspell it on the board. C-O-N-S-T-I-T. C-O-N-S-T-I-T. U-T-I-O-N-A-L. Constitutional isomer, also known as a structural isomer. Constitutional isomer has the same molecular formula, different molecular structures. Let's see an example of that. If we have, say, there you go. What molecule is that? It's an alkane. But what's it called? It's called what? Butane. C4H10, right? That's the molecular formula for that structure. I could also draw this. That has 1, 2, 3, 4 carbons. 3, 6, 9, 10 hydrogens. Wait a minute now. It's got the same molecular formula, doesn't it? But I think all of you, at least I hope you will, agree that this and this are completely different molecules, right? They have different shapes, different structures, different connectivity. So they're related because they have the same molecular formula, but they're not the same. How are they related? They're constitutional isomers, or structural isomers is also an accepted term. Okay? So that's one kind of isomerism. Structural. Pretty neat, huh? Structural or constitutional isomers. The other kind of isomer we have to talk about today, and we're going to come back to it, has a whole chapter devoted to it, it's chapter 5. It's called stereoisomer. S-T-R-E-O-I-S-O-M-E-R. S-T-R-E-O-I-S-O-M-E-R. Stereoisomer. Now, stereo, for those of you who may not know, because you know you have surround sound now, stereo used to be they put a record on. A record is that vinyl thing. Never mind. A CD. No, never mind. You download a song from... never mind. Forget it. Stereo means you have sound coming from 2 different speakers, okay? That's what it means. You also have, humans have stereo view. You have left eye and a right eye, okay? Your left eye and your right eye will allow you to see in the 3rd dimension, right? Do y'all know that? If you cover up one eye, you have an impaired depth perception, right? So stereo kind of implies 3-dimensional. Are you with me? So stereoisomer has the same molecular formula and the same molecular shape, or the same molecular structure, or the same structure. How are they different? They're different in how they're arranged in three-dimensional space. They're different in how they're arranged in three-dimensional space. But they have the same formula and the same connectivity, the same structure. It's very, very similar. But they're oriented differently in space. Go ahead.
Like that's the mirror, right?
Yeah, that's chapter 5, though. We're going to do something really easy today, and then in chapter 5, we're going to come back and slap that hard. 'Cause that's a whole chapter. It's a very important concept, too. Good for you. Okay? But we're going to go easy first. Unless you want me to start today. I can do chapter 5 right now. I'm comfortable with chapter 5. Now, a good example of a stereoisomer are things that are called cis-trans isomers. Now remember, we said earlier that double bonds can't rotate, right? We said that. They can't rotate. So if this carbon wants to flip over, that carbon has to flip over too, right? They're not independent of each other. So here, if you look at this structure carefully, you'll see that these two hydrogens, one's on this carbon, the other's on that carbon, right? They're both pointing, if you will, in the downward direction, right? This one's kind of pointing down, that one's kind of pointing down. Here, if you look down here, you'll see on this carbon, one of the hydrogens is kind of pointing in the upward direction, right? And this hydrogen on the other carbon is kind of pointing in the downward direction. So they're not the same, are they? They're extremely similar, though. I mean, you'll say that, okay, they have the same formula, no question about it. They have very similar structures, like this hydrogen is connected to that carbon, this hydrogen is on the same carbon, right? How are they different? Three-dimensional space. Here, the hydrogens are both pointing down. Here, one's up, the other one's down. So they're different in the third dimension. Are you with me? This is known as cis. Because both hydrogens are pointing in the same direction, you call that cis. Okay? If both hydrogens are pointing in the same direction, that is cis. And here, hydrogens are pointing in opposite directions, that is trans. Okay? Cis versus trans. Now, you've all heard these terms before, haven't you? Where'd you hear them? Biology. What'd you talk about in biology? I thought I was in trouble here with biology. I'm like, oh man, here we go. I'm like, biology, go back to my whole cellular career. Wash your hands after you talk about biology, people. I'm just joking. Cis and trans, where have you heard it? Come on, in the news. Well, that's, yeah, that. But even before that, we heard about it. What were we talking about? Come on, what were we talking about? Like, not even 10 years ago. McDonald's took them all out of their stores and replaced it with something else. Trans fats. Cis and trans fats, right? Remember that whole discussion? Trans fats versus cis fats? No? Trans fats were not under the radar. They were a huge deal. Wow, okay. Well, trans fats. You've heard of omega-3 fats, right? All right. Well, I got you there for one of them, right? Wow. All right. Oh, that's what we're going to do. But usually this lecture is better because everyone's like, yeah, what is a cis fat? You know. But I'm sorry. I just thought you guys would be more impressed by cis fats. No. Don't even try. I'm just hurt now. All right. Fatty acid. This is where cis and trans are usually heard of in our society. They're usually heard of in terms of fatty acids or fat, right? Now, there's two kinds of fat in the world, right? There's animal fat and vegetable fat, right? Animal fat is usually referred to as fat. Vegetable fat, we commonly refer to it as oils, right? They're the same compounds, though, right? Animal fat and vegetable fat are extraordinarily similar. Extraordinarily. The difference is plants, oils, have double bonds. Oils have double bonds, fats don't. Fats are what they call saturated. You've heard the term saturated before, haven't you? Saturated, I'm going to give you a little hint here. Saturated means alkane. That's what it means. So if you hear saturated, think alkane. You all heard unsaturated fat too, haven't you? Unsaturated fat means has a double bond. Well, it can also be triple bond too. but normally people are referring to double bonds. So unsaturated fat is an alkene. Neat, huh? So here we have an unsaturated fat because there's an alkene right there, right? Everybody with me? And these hydrogens are both pointing in the same direction, aren't they? So that's called a cis fat. Because this is cis. Right? The double bond is cis, so it's called a cis fat. Its brother, or its brother molecule, or sister, however you want to say it,
Is the first one a vegetable?
they're both from vegetables, yeah. This one here is also an unsaturated fat. How do I know? Double bond. Unsaturated means alkene. But notice, hydrogen up, hydrogen down, that's a trans orientation, right? So whenever you hear someone talking about trans fats in the news, what they're talking about is this. The double bond is trans, not cis. This, by the way, is natural. Fats naturally contain cis fats. This is unnatural.
So the trans is a process?
Yep. Usually. Now, is there examples of natural trans fats? Probably. But most of them are cis. Okay? Now, just because I have a minute and I think it's kind of fun to talk about this stuff, what does omega-3 mean? Does anyone know?
Fish?
They're found in fish, usually, yep. But you also find them in, I think, peanut oil, don't you? Or coconut oil, one of them.
And like in sunflower seeds.
Yeah, sunflower seeds.
3, 6, and 9.
Yeah, what's it all mean? What does omega-3 mean? Don't you ever watch the news and be like, yeah, that sounds really impressive, man. Omega-3, baby. Yeah. You know, people get like, they think they're smart because they start throwing out these big Greek words like omega.
Is there a ratio of fat?
No. Nope. What is omega? Just generally speaking, what is omega? If someone comes to you and said omega, what are they talking about? A letter. Which letter? Omega is which letter of the Greek alphabet? Is it the first or the last letter? It's the last letter of the Greek alphabet, right? Alpha is the first letter of the Greek alphabet. Omega is the last letter, right? So omega means go to the last carbon. Omega means from the end. Are you with me so far? So that's the omega carbon right there, the last carbon in the chain. You with me? That's all that means. Omega just means go to the end. And count back 3. 1, 2, 3. Omega-3 fatty acid has a double bond at the third carbon. You with me? Go to the last carbon. 1, 2, 3. Double bond right there. Doesn't mean much, does it? Just tells you where the double bond is. Omega-6, count back 6. Omega-9, count back 9.